Okay, so here's the drill. So we're going to go over that assignment. We're actually going to start centripetal motion today. You're going to have a short quiz over projectile motion on Thursday. Okay? It's going to kind of be like that one forces quiz, kind of at most like one page front to back. Mostly it's just going to be like one page. So, and there's only two variations on the theme. It's either a limbing problem or it's a ground-to-ground problem. That's it. Okay. Now, let's talk about the assignment from and the lab on last week. So here's what you cannot do, three of you in this class. If you happen to know how far something falls vertically and you want to find the Vy, let's say it falls, I don't know, 1.20 meters, and it takes, I don't know, 0.42 seconds to fall. Could you take 1.2 meters and divide it by 0.42 seconds to get the vertical velocity, Cohen?
No,
Why?
because it accelerates.
It's accelerating, okay?
You could. It would just be wrong.
You could, but it would be wrong. There's a lot of things you can say about that in life. You could do this thing, but it would just be wrong. So, and again, here's your mantra. I know you all are coming off of a long break. What happens in the Y stays in the Y. What happens in the X stays in the X. So even if you look at that equation that X equals 1/2 AT squared plus V naught time. Okay, that actually is applicable to both situations, because if you're talking horizontal motion, there is no acceleration. So distance equals velocity times time. If there is vertical motion, then you do have an acceleration, and then you have to decide whether or not you have an initial vertical velocity. All right. So make sure on that lab that what you should calculate is that Vx, that Vy, that overall launch velocity, and then you're going to calculate an experimental value for that angle, and then you're going to calculate experimental with theoretical minus experimental over theoretical times 100. This is the only time you're going to use the value that I gave you, okay? All right. When you get to that second question, and it's got, you're going to launch a cannon like this at a 45-degree angle, and then you're going to turn around. Now, here's the whole key to this. If you look on, if you're like big into trig functions, since this is a 45 degrees, first off, are you going to worry about the horizontal component of that velocity in this particular problem? No, you're not. It has nothing to do with it. So here's what you want to look at. So if you launch this thing at a 45-degree angle with some velocity, and you could either do smash mouth physics or you can take the elegant approach to it. If you want to do the smash mouth physics, like when I did the smash mouth physics, I said, oh, I'm going to let this be 30 meters per second. Okay, it doesn't make any difference, pick a number. But then it's only your vertical velocity that is going to determine that maximum height. Now here's the kicker. If you look at that vertical velocity and you're trying to find max height, since you don't have time, then you do this, okay? Now, obviously your final velocity is going to be 0, so basically it's a function of this. Now, here, if you're big into trig functions, if you look at, and this is what's on this yellow sheet, and this is something that Cohen alluded to, if you look at the sine of 45, the sine of 45 degrees is equal to root 2 over 2, okay? These are equivalent, and this is what I don't like about calculators, is that you lose a sense of the elegance of math. So if you're gonna look at finding this vertical component, that's gonna be that velocity times the sine of 45 degrees. Well, that's like saying, oh, that's that velocity times the square root of 2 over 2. These two things mean the same thing, okay? Sine of 45 times velocity is the exact same thing as saying that velocity times the square root of 2 over 2. It's an equivalent statement, okay? But you lose that because you're just so used to plugging numbers into a calculator. But these two are an equivalent statement. So now, if you wanted to, that's when you could plug that into here and go, okay, hey, what am I going to get there? Then, the next situation, you're just going to launch it straight up, either with some velocity or with the 30 meters per second, okay? I don't care how you do it, but you got to make a comparison between the two. Now, clearly, which one's going to go higher? One when you launch it at a 45-degree angle, or the one where you launch it straight up?
Straight up.
Straight up, because that's getting all that velocity. So if you look at this in terms of like a multiple choice question, where it's got, you know, for example, could it be, and you're comparing that, what is the maximum height reached by the same acrobat now? Well, what does your answer have to be bigger than?
Greater than y.
Yeah, it's got to be greater than y. Because if it's not, you're going to say, oh, no, I'm going to launch it straight up, but it's not going to go as high as if I launch it at a 45-degree angle. So, Cohen, could B be correct?
No.
Absolutely not. Okay. On the problem with the baseball, we'll deal with the table one in just a second. So, here's the story on this one. Here's the wall. You know, you're given information about the downward trajectory, and that wall was 7.5 meters tall, and it's moving at 36 meters per second, and you know that angle is 28 degrees. So, Gap Sean, what's the first thing I'm going to do with that velocity of 36 meters per second and that angle?
Make it into horizontal and vertical components.
Yeah, find Vx and Vy, okay? So, here's the assumption. Once you find that Vx, you know what that Vx is over there, okay? It's not going to change, okay? Same Vx is both sides. You don't have to do anything with that. Now, the tricky part here is that you need to figure out what the Vy is here when it lands. Now, here's the story. You all are used to saying, oh, something's falling from a maximum height, and it falls from its maximum height, and the initial velocity is 0. In your mindset, when you use that equation in a situation like that, you all are used to letting the initial velocity be 0. And you know how far it falls, and life is good, okay? But you can't do that here. You do know how far it falls. You are going to use that equation. But your initial velocity isn't 0. So you have to figure out the vertical velocity when it lands here. So if you know the vertical velocity when it lands here, you know that's going to match the vertical velocity that it had when it was launched. Now think this through. When this thing lands here, is it going to be bigger or smaller than the velocity that you had up there?
Bigger.
Bigger, okay? It's going to be a bigger value than this. If you get a smaller value, you're saying, oh, it's like the Tesla rocket. Oh, you fired the engines and it slowed down as it fell. Cool. No, this is not the rocket-powered baseball, all right?
Dang it.
Shocking.
That'd be sick.
And it's in free fall, and it's accelerating. So, anyway, both of your answers on that one with the baseball should be in the 30s. The launch velocity and the angle. All right, so let's talk about the problem with trying to land this thing, and we're going to do this in just a second. So here's the table, and we've got to figure out where to put that marble launcher launched at a 45-degree angle, and that's what I've got it set at, so that it goes up like this, okay? Now, here's the story. There's two ways you can actually do this problem. You can work it in pieces, or you can work it all at once, but you have to use the quadratic. So, one option is that you know the 45-degree angle, so therefore you can find your Vx, Vy, you can find your time up, and you can find your maximum height. Okay, clearly your maximum height has to be bigger than what?
0.7 meters.
0.7. If your maximum height isn't bigger than 0.7 meters, which is the height of these tables, you're not going to make it. It's like, what's the point? Okay? Cool. No, you're doomed to fail. So, one option is that you find your maximum height, and then you figure out how long it's going to take to fall, not all the way back down to the ground, but from that maximum height down to a height of 0.7 meters. And you can use that x equals 1/2 at squared plus v naught time, set that equal to 0. You know how far it's going to fall. You get that time, add the two numbers together, range equals vx time, you subtract out a meter. That's one option, okay? The other option is that you actually work it as a quadratic. And if you look at x equals 1/2 at squared plus v naught time, so you know what you want your x to be. So this is going to be your vertical component. This isn't like what happens in the x stays in the x. So you want this to be 0.7 meters. You know the acceleration, you know your vertical velocity, so you're going to have negative 4.9 times t squared plus that v naught of, what is it, 5.66? Yeah. Meters per second times time. And then you work it as a quadratic, and you get two possible roots, okay? So, what does somebody have as their distance for that problem?
3.09.
What do you have?
3.09.
Gap, Sean, what do you have?
4.71.
I like that better.
I think a really weird way I subtracted the time. I subtracted the time that it took to travel the distance over the table and the time it took to get to the table.
Okay.
I think that's what I did. Colin, who did it the normal way but still got the wrong answer.
I
Lost.
remember I did the quadratic thing, but I can't find it. on my
I see
picture.
a 4 over there.
That's in the time.
You just randomly see a 4.
Oh, I was looking for something that was close to his answer.
Probably.
Yeah, there's a 4.
Okay.
Time under time.
So this is always a little bit sketchy, but we'll give it a try.
1.82.
Berg prepares to shoot Will in the face from
No, we're not going to shoot Bill in the face. Okay, so you're gonna, can't spin this spin around.
Oh.
Sometimes we get this.
Will, you might be blocking.
So here's the deal.
I guess in the way.
What are your answers?
Gap, Sean said.
Oh, I nailed it. I'm so good.
7-1, Andy, you got 4. Okay, remember that.
Will, you might have to move your giant German head.
On the ground?
Professional cinematography. Oh, it's still.
A couple of round
Perfect.
numbers.
Set
I
it.
think 4.7.
Oh,
We're gonna see.
oh man. Go ahead.
Yeah.
Your turn.
I calculated the actual total time for the entire like thing. Yeah. It's
Nothing is real.
It's just a bunch of decimals.
Okay.
It's
all
a 2
fake.
centimeter discrepancy.
Yeah, he does not
Let's
exist.
see if we can get kind of close. All right,
Let's see.
Are you ready?
No.
You can hold it, you know.
I don't want to hold it though. This might be a hold situation, Will. Here, pass it to Danny.
What? No.
Danny's about to become the.
Yes, there we
Okay.
go.
Nice.
And it just
3,
scoops down.
2, 1.
Oh! It deeped it.
That was close.
3 seconds.
I think it was the tape measure's fault. It's off.
No, is it because
That's the closest I've ever gotten the first time. That actually took out the color.
Wow. Where'd the marble go? There it is.
Okay.
I was not expecting that.
Alright.
Hey, should we put water to add weight to the cup?
Now,
Go and you hold it then.
I think it's the tape measure and the ruler's fault. That's why it's off.
okay, so we'll back it up to 4.73.
That's what I got.
Oh.
No, that's why I said, we'll try it one more time.
Okay.
Will, you bad math. Nah.
The problem is the marble is fairly distorted, so,
Oh.
yeah, we were
Yeah, right here.
What a snap.
Well, and it's
We both
also
were
like not actually launched from the ground, so there's any number of things that are.
Oh, oops, I dropped it. From all of that.
Okay.
Was the dogs alright? And then dropped it.
Okay. Take down the camera back.
Wait, I'm trying to have a question. So finding you return, did you take?
Okay. Any other questions on that assignment?
For 2,
What?
Why am I dumb? We cannot explain that, Cohen. It is
If I knew
really.
the answer to that question, I could answer it and then make $1 million. Because parents would come to me, excuse me, why was my child dumb? And I would say, here's the reason, and then we would have a way to fix it.
Can you make up something?
There would be no more dumb children.
hypotheses, nothing.
Oh, when I was in Africa, true story, like, they believed in like traditional healers. And this gal was, she was a teacher, and her daughter usually got really good grades, but all of a sudden, like, her grades like fell off the face of the earth. And, so her mom took her to a traditional healer and said, hey, you know, she always gets good grades. She's failing her classes now, and so it's a whole process. You have to like throw the bones. The shaman reads how the bones land on the parchment. But he came back with the diagnosis that someone had stolen her brain. And for basically the equivalent of $500, he goes, I can put her brain back. So, okay. So he gives him the $500, the shaman says some incantations, puts the brain back, girl started getting good grades again. So maybe, you know, maybe
$500 USD?
Yeah. The equivalent of $500 US, you put the brain back.
Wait, what country?
Botswana, just north of South Africa. We'll talk about that. Anyway, okay.
Someone stole my brain.
Yeah.
That's why you're stupid.
Yeah. All right, anything else? Going once, going twice, sold. Get that handed in.
Is the coefficient for number 2 greater or lesser than 1.5?
For which one?
Number 2.
Multiple choice on the
We talked about this, Colin.
Danny, we
baseball?
talked about this. What
No,
are you doing?
for the cannon
Oh,
firing
okay.
acrobat.
Danny, we talked about this.
It does involve a two.
That's what it was?
That's so helpful.
We talked about
Somebody
it.
did it.
I
D and N.
Everyone
And I
else
just didn't look at it.
seemingly has a different answer than I do, but I plugged in it and I don't understand.
So Bird, sorry, Bird. Here's the problem. None of us got A or B, so you didn't help any of us by telling us not A or B. All of us got C or D.
Well, pretty
Actually,
much
sorry, everyone got D other than
it's
Colin.
D. Yeah, it's D.
Well,
my brain
actually,
says it's D, but like,
Danny actually had A.
Danny!
Someone convinced me
Could you
like last week. Someone
could
said,
you
oh,
explain
it's
to
A
me,
and D.
like,
Because
why
they
I'm
looked at it,
wrong?
it was like, okay, and I never was
Once
it
we get,
since.
let me
Yeah,
get started
thank
on
you.
the assignment and then.
And it's someone from fourth one.
Okay. All right, so here's the next big thing. And let's start with this idea. So I've got this rubber stopper and I'm moving it around over my head like this.
rubber.
Okay? So once I get it up to a constant speed, here's the question. is this accelerating at this point?
No.
Yay or nay?
Nay.
Nay.
Are you
Right.
moving your
Wait. Wait.
I'm just moving my hand just to keep it moving.
Yay.
To keep it
Right,
at
'cause
constant velocity.
Yeah, if it's not accelerating upwards or downwards, then there is a force acting on it to counteract gravity.
I don't know. Well, clearly, it's not falling, right? If I do this, it falls. So,
But it is turning, right? Isn't
it
that
is,
also?
it is very much spinning around in a
Centripetal
circle.
force.
Then isn't that accelerating?
I don't know, this is
Oh,
my
didn't he
question.
say that turning was accelerating like
Yeah.
a long time ago?
You at one point mentioned something about turning is
It's
accelerating.
either accelerating or it's not.
It's accelerating.
Yes.
Final answer.
It's not.
Locked in.
It is accelerating,
That's my gander. Yes.
okay? So, if we assume that it is accelerating, what's the direction of the acceleration?
Left.
Circle.
Yes.
Clockwise. Counterclockwise.
So, this is looking down from on top.
You have to reconnect
Okay.
again.
So you, and
The
it's
connection.
going around like this, right?
Your TV is being autistic.
It's being like Cohen.
I would just like to say that those answers to what direction it's accelerating it was the most intelligent thing I've heard in a long time.
That doesn't say much.
He said, "What direction?" and I said, "Circle," and the rest of you gave yes or no's.
Yeah, none of which were applicable. Okay, so this is looking down from on top. Okay, so imagine you're an observer looking down from on top. Here's your three options for the acceleration. The acceleration is either in the direction of motion, it's either outward, or it's inward. Those are your three options. Okay, now to settle that, bring the camera, let's go to the back of the room. So, go on, go on.
Let's go, fellas.
Oh, I lied.
Oh. Oh.
That's a new thing.
New thing, yes.
So if you get bugs,
It's like
Okay.
the blood of your
if you get bugs ever, and I want to.
That's the blood of Cohen.
So, I've got a 100-gram mass on the end of the string, right? And a loose pulley.
Cohen. It's gonna be your blood if you do something wrong.
It is my blood. You didn't know.
Oh. Hey, we
Okay.
got a lot of things wrong.
So this is what's known as a liquid accelerometer, and no, that isn't blood from the freshman,
I thought it was
It's blood from
Cohen's.
Cohen.
or Cohen's.
Aw.
You
Okay,
sure?
so I'm gonna let go of it, and obviously it's going to accelerate in that direction. So when I let go of it, there's three things that can happen to the level inside of here. It could just stay level because it's not being acted upon by the force, okay? So it's just gonna maintain a constant velocity. It could move forward because it's gonna be moving in that direction, so that's the direction of the force, and that's gonna push that forward. Or it's gonna move to the back, okay? Those are your three options. Level, forward, back.
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 Inertia. It wants to stay there.
Back.
Forward, but the liquid stays back.
Okay?
I'm
So,
gonna let go on the liquid.
I'm gonna let go of it, okay? Alright? So as soon as that begins to move, it's subtle, right? So I let go of it, and we get a little bit of a tilt. Now, if I put a 200-gram mass on the end of it,
Berg catapults his liquid accelerometer.
I'm gonna tie it to a
100.
string and then fling it in a circle to see.
just chill out.
Are you gonna
Okay.
tie Will to a string and
Okay.
circle?
Accelerometer
That's how
down.
hammer throw works.
Okay? So now when I do it, what happens to the angle?
It's steeper.
Steep. So here's the story. So let's just look at this. Does this liquid have inertia?
Yes.
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 It has stuff.
So it wants to remain at rest, right? So imagine that I could do this, and at the exact instant that I let go of the weight, I could make the back of this disappear. Okay, so I'm going to let go of it. I'm going to make the back of that go away. What would the liquid do?
I'll follow the back.
Would it get pushed out the back, or would it just stay in place?
Pushed out the back.
Well,
It would stay in place.
it would
It
stay
would
in
just
place,
stay
and
in
the
place,
and the cart
right?
would move
Because the
away
cart
from
would
it.
accelerate out from underneath it, right? It would just stay in place. So here's an important concept.
Sorry, it was cool.
So here's an important concept. Is there something in front of the cart exerting a force to push the liquid towards the back?
No.
No.
No. There is nothing in front pushing it towards the back, right? It just wants to remain at place. The back is making it accelerate forward. Now, this is important. What was the direction of the acceleration?
Forwards.
Forward.
Front.
Which direction did the water level move?
Backward.
Backward.
So it moved in the opposite direction of
Acceleration.
the acceleration. And the bigger the acceleration, what happened to the angle?
Steeper.
Steeper. So here's what I want you to realize. If you're accelerating, this moves. And it moves in the opposite direction of motion. And the bigger the acceleration is, the steeper that becomes. Got that?
Got it.
Okay. Now, let's go back up front. Cohen, I'm going to need you for a second.
Oh, yay. Break prepares to hit you with a bowling ball.
He caves your head in with Hank.
So, yeah, I just need you to sit there.
Okay.
And then hold this out level. No, like that.
Oh,
Like this, like that. Okay, so here's what we're gonna do. I'm gonna spin Cohen around, okay? Level,
Oh,
okay? I'm gonna spin Cohen around. Now, if it's not accelerating, what's this gonna do?
Stay the same.
It's gonna stay the exact same level, okay? Because you initially said, oh, the rubber stopper isn't accelerating. And if that was the case, this is gonna stay completely level. But then you changed your minds, and you said, Cohen searched the dark recesses of his mind and said, oh man, Camp said something about moving in a circle, you're accelerating. So then you all changed and said, oh, it's accelerating. So here's my question. I'm gonna spin Cohen around in a circle. If you're right that it is accelerating, either the water level is going to move towards the inside or the water level is going to move towards the outside.
No.
Going?
Outside.
It's gonna move towards the outside, right?
Why?
Outside.
Because centripetal force. You go circle, thing go away.
Disc is.
Hammer.
Okay, you ready? So as he slows down, what happens to the angle?
I was right.
It decreases.
It becomes less. So the faster he spins, what happens to the amount of centripetal acceleration?
It increases.
It increases, okay? And as he slows down, it becomes less. Now, which direction does the fluid move?
Away.
Away. So what's the direction of the acceleration? Inward.
Oh, wait, yes.
Inward,
Yeah.
right? Okay, thank you. Well done. All right, so here's the story. So, when you have, and we're gonna call this A sub C, which stands for centripetal acceleration. Now, there's centrifugal and then there's centripetal. Centripetal comes from the Greek word meaning inward seeking, okay? Centrifugal means outward seeking, okay? So this is why it's called centripetal acceleration, because it goes towards the center. So let me hand out this, Danny. Let me hand out these lecture notes, okay? Don't flip out, they're just lecture notes. Danny, you allergic to centripetal motion?
No, I think I'm allergic to Cohen.
Bro, if you were allergic to me, you would have died.
Yeah.
Well, it's only season. It's not that bad of an allergy.
It's a seasonal Cohen allergy.
Yeah.
Seasonal
This
Cohen
is,
allergy.
in the current grade book, right?
Well, yeah, it's gonna go in this 9 weeks, yes.
Okay.
I'm so proud of you.
Because the only
Oh,
time I
like, this
sneeze
is-
the
this
most
is-
is around Cohen. Because
Yes.
that's school.
I know, it's weird, I have to 100%, but I always like this one.
Okay, now here's the odd thing about centripetal acceleration. We're gonna spend a lot of time talking about it, and you have one equation on your equation sheet, and that's v squared over r, okay? That's it, one equation that you have for centripetal motion, v squared over r. We're gonna come up with a bunch of other ones, but that's the bread and butter. So, here's the story.
I like how this equation sheet is just like, here's one maybe useful equation. Everything other than the first unit. It's like, here's one maybe useful equation, and the rest you're just gonna have to memorize anyway.
Or at least derive, but it does, usually it's pretty simple derivation. Now, units. Danny, what units is velocity gonna be in?
Meters per second.
But that's gonna get squared, so that's gonna get you,
Meters squared divide over second squared.
and then we're gonna have a radius divide in,
Meters.
so we're gonna lose one of the meters, we're gonna get,
Acceleration, percent squared.
ooh, how cool is that, right?
Wow.
Cool. So,
pretty
if you look on the lecture notes, so as this rubber stopper is going around, remember, there's 2 parts to any vector quantity. What are the 2 parts to any vector quantity?
Magnitude and direction.
Magnitude and direction, okay? So up to this point in time, until October 15th at 8:15, we've only talked about changing the magnitude. We've talked about, oh, what happens when I take the rubber stopper and, where'd the rubber stopper go?
It's underneath the paper.
There it is. So we've talked about, oh, I drop the rubber stopper, or I throw the rubber stopper up in the air. Speeds up, slows down. I push it, and then it slows down. Up to this point, we've only talked about the magnitude. Now we've got to talk about the direction. So this boils down to Newton's 3 laws of motion. So the first law says basically Mother Nature wants to maintain any state of velocity, okay? Notice I didn't say speed. Mother Nature wants to maintain a constant velocity. And there's 2 components to that velocity. There's magnitude and direction. So this, if I look at this as this thing goes around, what you have to ask yourself, does Mother Nature want to travel in a circle? So it also boils down to this idea of Jedi-Stoffel law. You stop the force and you watch what happens. So if I stop pushing that rubber stopper, it comes to a stop. Oh, that means there's a force acting on it, because otherwise it would keep going in a straight line. So if I spin this thing around and I let go of it, what's it going to do?
Fly away.
Fly in
It's going to
direction.
fly away. Why?
There's no more acceleration inward.
Yeah. So therefore, what does it do?
Accelerate
out.
away.
It travels in a straight line at a constant speed, because Mother Nature goes, hey, look, you're not applying a force, I'm not going to play this game. So Mother Nature doesn't go, wow, I like circles. Because if Mother Nature liked circles, it would be cool. If Mother Nature liked circles, I could let go of that string, and what would happen?
It would keep circling.
Yeah, it would just stay in orbit around me, okay? Which would be cool. Like, I could let go of the string and be like, this thing would just keep going around and going around. It's like, cool, right? It would be the ultimate physics demo. It's like, what happened? Oh, I'm my own solar system. Okay, things orbit me.
You just spin for a little bit,
Yeah,
or like you spin something around yourself and then just let go. And
yeah. I imagine shot put or discus,
Hammer throw.
hammer throw. Okay, you
Yeah.
let go of it. It's like, oh man, it's going to stay in orbit around me. Now,
next time you go out in public, it just until it hits.
so here's the next thing that you have to ask yourself. Okay, I have to have a force. So you all were used to F equals ma. Well, with centripetal force, that's going to be centripetal force equals mass times my centripetal acceleration. So if I take Hank and swing Hank around on the end of a string, what's going to happen to the amount of centripetal force I need?
It'll be a
It's
lot.
gonna be quite
It'll
a
be a
lot.
lot bigger.
Straight
Okay.
break.
Now,
The poor string.
obviously, if you're going to have something move in a circle, you have to have a force. Okay? Because without a force, you're not going to travel in a circle. So the question is okay, what are the sources of centripetal forces? A little poetry here this morning. So one option, obviously, is that you could have tension. Okay? It's a hammer throw. Okay? You've got a chain. You've got a rope. You've got a cable. You've got something that's moving around in a circle. Okay, cool. Right? Now, I'm guessing at some point today, when you all drove to school, you had to make a turn. Right? I'm guessing nobody drove completely straight all the way to Mays High School. Okay? How do you get to Mays? I drive straight and then I stop. How do you get home? I back up. Reverse direction. Do you change? No. I just go straight. So, when you made that turn, did you accelerate?
Yes.
Yes. So what allows you to accelerate?
Force.
Turning.
Centripetal force.
What creates the centripetal force, though?
The steering wheel.
No.
Centripetal motion.
No. Let me ask you this. What if we had an ice storm overnight and everything was a sheet of ice?
The friction between the
Ah,
ground
friction!
and the tires.
Okay? Because turning the steering wheel in and of itself is not going to allow you to turn. But if you turn the steering wheel and your tires have friction, same thing is going to happen when you all walk in this room. Okay? I'm guessing you all were walking straight and then you had to make like a left turn. When you made that left turn, you accelerated because you changed the direction of your velocity vector.
Oh, I live in the walls.
So then you got friction. Now, on a cosmic scale, here's the sun, obviously not to scale.
What?
There's the earth. Are
That's
we
gotta be-
accelerating around the sun?
Yes.
Yeah.
Mm-hmm.
Yes. And that's a good thing. Because what's your alternative?
Flying
Constant.
off into space.
We become like the rubber stopper, okay? And we
The
go
world's
flying
the
off into
largest
space.
black
NASA sends out, a bulletin that says, hey, this whole gravity thing, we don't have it anymore, okay? We're screwed. Because we're gonna get awfully cold, awfully dark, really, really fast. Because we're just gonna go doink. So, third one's gonna be gravity. Now, in every situation, whether it's the earth, the rubber stopper, whatever, the direction of the centripetal force and this direction of the centripetal acceleration, and there's two parts to this. Listen to me. There are two parts to this direction. The first one is that it acts inward, because that's the direction that you're continuously changing the velocity vector. Okay, so inward is the first part. The second part of that definition is that it's at a right angle to the instantaneous velocity vector. So when I ask you, and I'm going to, what's the direction of your centripetal force? Oh, it's inward and at a right angle to your instantaneous velocity vector. Those are the two parts to this. But here's the problem. This doesn't match reality. It's a great mathematical model, and you go, oh, it makes sense, okay? But it flies in the face of reality, and I'll show you why. this makes no sense in reality. Okay. So let's say Cohen takes the money that he earned over the weekend and he buys a Jeep. Okay?
I would not buy a Jeep. I hate Jeeps, but okay.
Just stay with the story, Cohen. Stay with the story.
Can't drive on the highway
Okay.
very well.
He buys a Jeep, and this is looking down on top of the Jeep. Okay?
Does the Jeep get wrecked?
Shush. My story, not yours. So Cohen's driving along in the Jeep. There's the front, there's the steering wheel. Cohen being the safe driver that he is, he has both hands on the steering wheel at all times.
10 and
Okay? 10 and 2. So Cohen's driving
Such a good
along,
driver.
and Cohen takes a sharp right-hand turn. Okay? So Cohen's here. This is looking down on top. Okay? Cohen, what are you going to experience inside the Jeep?
Upside down as it rolls.
No, you're not going to roll. You're just going to take a turn.
Oh.
You're gonna drift.
Yeah, are we Tokyo drifting this thing or like?
Just, you're taking a turn. Shut up.
I'm gonna lean. Well, I turn this way and then I lean.
Inertia. It's
It
Okay.
pulls- Inertia. I want to keep traveling in a straight line.
No. That's not the question.
I don't know.
It's not the question. What are you going to feel pushed up against the door?
Yeah.
Yes. Okay? If you're Cohen and you're inside the car, you're going to feel like some magical force field is pushing you against the car door. Okay? That's what you're going to feel. It's like, oh, right? Okay? You're going to feel that. Now, but if you think it through, and this is what centrifugal means, okay? Centrifugal force means outward seeking, okay? So here's the story. If that was actually true, let's think this through. So Cohen makes his turn, and he is legitimately going to feel pushed up against the car door.
It's a hard turn.
But here's what you think through. It's like, okay, if this actually was going to happen, there would have to be a force field inside the car that you can't see, that's emanating a force that you can't see, that interacts with your body, because it isn't like we would see like his clothes get distorted, like it's pushing him against, okay? You're not going to see that. It only activates when you turn, and it senses that the faster you're going and the smaller the radius, the more it's going to emanate this force. But as soon as you straighten it out, oh, it stops again. So if you look at all the magic that would have to happen for this force to push Cohen against the door, it doesn't make any sense. Okay? It doesn't. But now, let's look at this. We like Cohen, we won't do this. But what if we took off the door and the seatbelt, and we put magic frictionless seats inside the Jeep?
When I turned, everyone is leaving the vehicle.
Cohen turns, what's Cohen gonna do?
Fly out.
Cohen's gonna keep going in a straight line, because he has
Inertia.
inertia, okay? So basically what's happening is that the car door is getting in the way of Cohen turning into a projectile. Okay?
Dang it.
That's what it's doing.
That's a very
So-
scary projectile.
There's nothing inside
Ugly.
pushing him. What he feels is the action-reaction force of the door pushing him inward and his body trying to maintain a straight line. It'd be the same thing if Cohen was sitting here and I came up from behind him and I pushed the chair. Cohen would go like this. Is there something in front pushing Cohen backwards?
No.
No, there's not. Okay? But his body is going to feel that. It's like, oh man, I'm being pushed into the chair. No, your body just wants to stay at rest. The chair is pushing you forward. You're pushing back on the chair with an action-reaction force.
So what I'm
Okay?
hearing is that every time I turn in a vehicle, my body is yearning to become a projectile.
Basically, yes.
Okay. Which is scary, but is it or is it funny?
It's up to you,
Depends.
however you view it. Okay,
I just like to imagine every time I turn,
Now.
something flying away.
let's talk a little bit of math. So, you know that mu equals force friction over force normal, right? Okay, you know that's gonna happen. So, if you look at your car as it makes a turn, we said, as that car is making a turn, if you look at it kind of like sideways, okay, so here's like kind of a three-dimensional view of your car.
Nice car. I'd drive it.
It's because it's a truck.
And-
It's on the 2025 Bugatti.
It's coming around like this, right? What does your car want to do?
Go in a straight line.
Goes in a straight line. So, in this situation, the force friction is what's creating the centripetal force. Now, if you're on a flat surface, that force friction, instead of force normal, we can put Fg. Okay? It's an option. Now, if you want to go to another option, you can go, oh, well, that's mass times centripetal acceleration. Okay? Well, Fg is going to equal to what?
Force normal.
Mg, right?
Sure.
On a flat
Yeah,
surface.
force normal. Yeah.
True? So your masses cancel out. You can look at this as the ratio of centripetal acceleration to
Gravity.
gravity. Okay? Now, here's the next thing. What's your theoretical limit of mu?
One.
1. So if your tires have a coefficient of friction of 1, what's your maximum centripetal acceleration you could get? 9.8 meters per second squared.
And
Okay.
anything more than that,
Bad things are going to happen. Now,
Something's
stop
wrong.
that, because if it goes too long, then it gets weird. I'm going to go